Okay, so I'm happy to be back in this spot, and I'll be giving the next like 7 lectures or so. This module of the course will be about one way to think about it is multi-agent systems, and we'll see the connections in a minute. Another way to see it is the intersection between computer science and economics, and the application of work in that intersection to artificial intelligence. So let me just talk briefly about this multi-agent systems viewpoint. So multi-agent systems is an important sub-area of AI that generally thinks about designing systems that are populated by autonomous software agents that can interact and make decisions and negotiate and so on. There's a lot of work in this area over decades, but from a very biased viewpoint, the kind of things we'll talk about are some of the main tools that people use to reason about multi-agent systems. So I'll try to illustrate this to you, like just how important things like game theory and social choice are in multi-agent systems. So these 2 books are I would say the 2 most popular books in multi-agent systems. One is a book by Yoav Shoham, who's a professor emeritus at Stanford, and Kevin Layton Brown from the University of British Columbia. The other is by Mike Wooldridge from the University of Oxford. So if you look at the table of contents of the book by Shoham and Layton Brown, this is the table of contents. So it has 14 chapters, and 8 of them are on game theory or social choice. Okay, so you can see like the way that these areas have within multi-agent systems very clearly in this table of contents. Now, the book by Mike Wooldridge, actually, it does have some game theory and social choice and so on, but in terms of fraction, it's a much smaller fraction of the content of the book. However, I just pasted Mike Wooldridge's 2016 publication list. So he's published many papers in 2016, and all of the ones marked with an arrow are papers about game theory. Okay, so even the other book written by Wooldridge, even though it doesn't have a lot of game theory in it, Mike has been doing a lot of work on game theory in recent years. So this is really something that's become very, very prevalent in the multi-agent systems community. Okay, so with that, we'll just devote this lecture to talking about some of the basics of game theory, especially Nash equilibrium, without applications this time. And then starting from next lecture, we'll talk about new game theoretic concepts, but interleaved with applications, really driven by applications. Okay, so like I said, starting from the very basics, we'll talk about different types of games. The most standard model is called a normal form game. In a game like this, you have a set of players that will denote by capital N, and the players themselves will be integers 1 to n. So we have n players. And each player will have a strategy set S. So to simplify notation, I'm assuming that everybody has the same strategy space, can choose from the same action set. But in general, they could have different strategy spaces. This is actually without loss of generality, because you can basically say, take the strategy space to be the union of all of the individual strategy spaces, and horrible things happen if some players play stuff that's outside what we wanted to play. So we'll just use this for notational convenience. Now, for each player I, we have a utility function, UI, that takes as input what I call a strategy profile. So this is a collection, a vector of n strategies, 1 per player. And it outputs the utility to player I when all of the players play those strategies. Okay, so for a vector of strategies, UI says, what's the utility of player I? Okay, so I want to give you a very simple example to just illustrate this model. It was actually taken created by taking screenshots of this movie that I found online it's sort of related to a TED Talk. So the organization that does TED Talks also has some educational videos about particular topics. And this is a really cute animated video that they created. So the story is that our name is Ed, and we are selling ice cream at the beach. And then one day our cousin Teddy shows up, and he has an identical ice cream bar that he calls Ted Bar instead of Ed Bar. And again, this is where Ted, as in TED Talk, comes in. Now, the importance of the fact that his ice cream is identical is that we're basically assuming that people don't care who they buy from. All they want is to buy from the nearest vendor. So if they're closest to our shop, our stall, then they will buy from us. Otherwise, they would buy from Teddy. Now, so what we do, we're sort of friends, so we split the beach in half. We set up at the 1/4 point, and Teddy sets up at the 3/4 point. So think of the beach as the interval between 0 and 1. And we're basically going to assume that the customers are uniformly distributed over the beach. Okay? So what this means is that 50% of the customers are going to buy from us at the 1/4 point. So basically everybody from the half point south will buy from us, and everybody from the midpoint north will buy from Teddy. So it's 50-50. Now one day Teddy decides to be clever, and instead of, as usual, setting up at the 3/4 point, sets up at the 1/2 point. So this is a problem now, right? Because this is the situation, and now we're only serving 37.5% of the customers. Right? So just the guys, the people up to the point between us and Teddy, and south of that will go to us, but then the rest will go to Teddy. So that comes down to 37.5%. Okay, so we're going to revisit this game later and see how to solve this game. But what I want to do right now is just give the formal model for this game using the notation that we introduced on the previous slide. So the set of players here is going to be 1 and 2. We just have 2 players. The strategy set is the interval 0, 1. So you basically can choose any point on the beach to set up. Now, what's the utility function? So the utility to I, when I chooses a point Si and J chooses a point Sj, is as follows. If Si is smaller than Sj, then basically I will get all of the customers from the bottom up to the midpoint between Si and Sj. So the total utility, the fraction of customers I get, will be Si plus Sj divided by 2. Everybody from 0 to this midpoint. If Si is larger than Sj, then I is getting the northern customers. So it's everybody from 1 down to the midpoint between Si and Sj. So the fraction of customers, when they're uniformly distributed, is 1 minus this midpoint, which is Si plus Sj divided by 2. And we're going to assume if they chose exactly the same point, then customers are going to choose uniformly at random who to go to, and then they each get utility 1/2. Okay, so that's sort of just using the notations we had before. That's how we represent this game that we just talked about. And like I said, we're going to revisit this game in maybe half an hour and think about how to solve it once we introduce the relevant concepts. Okay, but before that, I want to start with a more basic game and one that is really well known. So can you raise your hand if you've heard of the prisoner's dilemma before? Cool, most of you, right. So yeah, let's go over this quickly. This is sort of a pretty well-known concept. So the story is, 2 men are charged with a crime, and they're told by the police that, or sort of know from their contacts, that if one rats out and the other doesn't, then the rat will be freed. So basically, all of the blame goes to the one to the guy who didn't rat out, and the guy who was nice to his partner will be jailed for 9 years. So he gets all of the blame. If both of them rat out, then there's quite a bit of evidence about both of them. So they sort of share the blame to some degree, and they both are jailed for 6 years. But they also know, I guess the police doesn't tell them this, is that if neither one of them rats out, then there isn't a lot of evidence against them, and then they'll both be jailed only for 1 year. So here's how we represent this game as a normal form game. This is the graphical notation for a normal form game. So the idea is we have one player choosing a row, the other player, player 2, choosing a column. And for each entry, we have 2 numbers, where the left is the utility to player 1, to the row player, and the right is the utility to player 2, which is the column player. So, the usual terminology for strategies in the prisoner's dilemma is cooperate and defect, where cooperate is basically saying the player is not ratting out, is cooperating with his partner. Defecting means his screwing his partner over and ratting out. And, so the numbers just represent our story. So we're saying, if both of them don't rat out, both cooperate, they both get 1 year in prison. If one of them cooperates and the other defects, the one who defected goes free, the one who cooperated gets 9 years in prison. So this is cooperate with the other player, not with the police. And if they both defect, so they both rat out each other, they both get 6 years in prison. Okay, so that's the game. And sort of the standard question about the game, it's sort of a game where there's a pretty decisive answer to what you would do if you are rational. Right? So what do you think? What would you do if you had to play this game? Would you cooperate or defect? Defect? What? So why? Who said defect? Ashwin?
So what I thought was that if each of them assume that the other one picks something randomly, that's probably not a very good way to go because the other one will try to optimize. But if you say that the other one is not randomly, you just take the utility average based on that for you in those scenarios.
Okay, that's a good point. So Ashwin is saying, if we assume the other player was playing randomly, then you can you can compute the expected utility and see that it's better to defect and cooperate. But there's an even stronger argument. Alex?
I mean, if we are thinking about each individual as like each person with his own interests, not like maybe he's my brother or something like that, like on his own interest, then if he picks, let's say, cooperate, then I will defect him and I get 0 years, and if he picks defect, then it's better for me to pick defect as well. So each situation is better for me.
Perfect. Right, so Alex is saying, in fact, whatever the other player does, it's always better for you to defect. Right, so let's look at this again. If, let's say we're the row player, if the column player plays cooperate, we're basically choosing between 1 year in prison and 0 years in prison, so we're better off defecting. If the other player chooses defect, we're choosing between 9 years in prison, 6 years. So again, we're better off defecting. Okay, so this is like the crazy thing about this game, where the best outcome for both players overall is when they both cooperate and only get 1 year. But from a rational viewpoint, you're always better off defecting. Right? So each player, if they think rationally, they're like, in any situation, whatever the other guy is doing, I should defect. But then, if the rational both end up defecting, and then they both get 6 years in prison, which is a bad outcome. Right, so this is why this game is so well studied, because it's such a counterintuitive phenomenon where the rational thing to do goes, and it's not only rational, it's just you're better off in any situation, whatever the other guy does, but that leads to a really bad outcome. This is related to a phenomenon. There's a lot of work trying to circumvent this thing. Coming up with new game models where this wouldn't happen. But there's also it's sort of become a part of popular culture, and there's a lot of talk about different situations that are like the prisoner's dilemma. So another kind of situation which is similar is called the tragedy of the commons. So this is something that was introduced in the early 19th century. I think it was 1830 and something. And the motivation was cows grazing in some common grassy area. So if each herder just lets his cows graze without any limit, then what could happen is the grass gets so badly depleted that it doesn't grow back. So, when everybody sort of doesn't control their cows, that's really bad for everybody because you just won't be able to graze anymore, like nobody. But, from an individual viewpoint, you're like, okay, I mean, my dominant strategy is to let my cows eat as much as possible. If others are behaving well, that's great. Things will continue and I'll get like more grass for my cows. If others are behaving badly, then okay, the grass will be depleted anyway, so why not participate in like depleting it? So it's sort of a dominant strategy, the rational thing to do, even though it just ruins this common resource. And these kind of situations, people have talked about them, like I said, in many different contexts. So here are some of the popular ones. In presidential elections, you can think of cooperate as using only positive ads and defect as using negative ads. So the socially best outcome is if everybody just says nice things about each other, and and then the faith of people and their leaders is not ruined. But if the other guy is cooperating, if you use negative ads, then that's sort of much more effective, right? You're the only one doing it, so everybody is like, oh, that other candidate is really bad. And if the other candidate is defecting, then again, like you really want to defend yourself and use negative ads as well. So it's again like whatever is happening, you want to defect. Nuclear arms race, you can think about the Cold War. So the players would be the US and Russia, and then cooperating is destroying your nuclear arsenal, and defecting is building your nuclear arsenal. And again, if the other player cooperates, and you're the only one with nuclear arsenal, you're in great shape. If the other guy has a nuclear arsenal, of course, you want to have one as well. So again, that's how we ended up in this Cold War situation. Climate change is maybe even closer to the tragedy of the commons. So the common good is clean air, but then, and the players are countries, so you can either curb CO2 emissions or not curb, and then it's again the same kind of situation. Okay, but what I want to show you is a really, really cool example. I just love showing this video when I teach the basics of game theory. So this is from, I don't even remember how I first came to find this. It's from some British TV show called Golden Balls. And apparently, I've never watched the show. I've just watched a few videos about the relevant part that I'll show you. So it has it's like a quiz show. There's some stage where they answer questions. They get some, the contestants get some pool of money. But then the interesting part is that there's another mini game that they play at the end, and it works as follows. Each one of them has 2 balls, either split or steal. Now, if they both choose split, then they split the money that they earned. If one of them chooses split and the other chooses steal, then the guy who chose steal gets all of the money, and the guy who chose split gets nothing. And if both of them choose steal, they both get nothing. So these are the rules of the game, quite similar to Prisoner's Dilemma. And the nice thing is they have a phase where they talk to each other and basically try to convince the other player they're going to choose split. It's always like that. And and then they choose without showing the other player, and then the balls are revealed. So I want to show you one of the nicest examples of this. And I'm going to start from the phase where they talk to each other, and then they're going to choose their strategies.
Abraham, I want you to trust me. 100% I'm going to pick the steel ball.
So,
I'm going to choose the steel ball. I want you to do split, and I promise you that I will split the money with you.
Well, after you take steel,
Yeah.
you're going to take steel.
Yeah.
I'm going to take split.
Yeah.
So you take the money.
And I will split it with you.
After the show.
Yeah. I promise you I'll do that. If you do steal, we both walk away with nothing. I'm telling you 100% I'm going to do it.
I'll do that. Well, I'll give you another alternative. Why don't we just both pick split?
I'm not going to pick split. I'm going to steal. Abraham, honestly, 100% going to steal.
It's in your nature to steal.
No, I'm honest, and I'm going to tell you.
You're honest.
I am. That's why I'm telling you I'm going to steal. If you do split, then I will split the
I
money.
can't see myself doing that.
Okay, well I'm going to steal, so I'm going to leave with nothing.
Where's your brains coming from? I can't work out.
I know that I'm a decent guy, and I will split the money with you.
Well, we should just both split then.
No, I'm going to do steal.
There is no legal
I know there is.
for him to give you the
Of
money.
course. If I gave you my word, now let me tell you what my word means.
Okay.
My father once said to me, a man who doesn't keep his word is not a man. It's not worth nothing. Not worth a dollar.
I agree. So, Abraham, I'm going to steal. I'm going to steal. And we both walk away with nothing. Because I've told you my intention, and I've told you that I will split the money with you, Abraham.
If I gave my word I was going to split, I would split. And you're going to take still. So,
The only way you can guarantee to walk away with 6,800
It's by
is to
sharing.
guarantee that you both put the split ball in. And I do now have to push you for a decision. It's a tough one.
we've lost it. We've lost everything.
Okay. Class then.
You're walking away with no money because you're an idiot.
No, that's all right.
You're an idiot. That's what you're an idiot. You're an idiot. That's what you are.
This can go on all night, and these people are going to get up for breakfast. Nick, choose split or steal. Abraham, choose split or steal. Now, please. Choose a ball.
Right, I'll tell you what, I'm going to go with you.
Okay.
I'm going to go
I
with
promise you I will split.
You cannot change your balls now. Split or steal. Yes! Steel's roll call split to each and select 6 plus
Okay, cool. So that's just one example of game theoretic reasoning in real life. So of course, like here, what Nick did is sort of he went outside the game and said, you know, there's this other strategy where I'm going to split with you after the game, and that's what led to this interesting scenario. Okay, so let's talk about another game. I call this game the Professor's Dilemma. This game works as follows. There are two players, the professor and the class. As the professor, I have two strategies. I can either make an effort when I prepare my lecture, or I can slack off. And as the class, you have two options. As students, you can either listen or sleep. So if I make an effort and I create a good lecture and you guys listen, we both get utility 1 million. So you know it's going to be awesome and everybody is happy. But if I make an effort and you sleep, you will get utility 0. You don't learn. I get negative utility because I spend this effort and like nothing came out of it. And similarly, if you listen but I slacked off, you spend this effort but didn't get anything out of it, so you get minus 10, I get 0. And if we both slack off and sleep, we both get utility 0. Okay, so you know the game is kind of similar to the Prisoner's Dilemma. It's also 2 players, 2 actions each. It's symmetric. And you know the question is again like what would you do? Okay, but an even more basic question is is there a dominant strategy in this game? And if yes or if no, why? Priya?
No. So if let's say I'm the professor for fun. So if if I make an effort, or if the class listens, then like I know the class is going to listen, then I'm going to want to make an effort. But if I know the class is going to sleep, I'm going to slack off. And so like depending on what the class does, my option.
Excellent. Right. So Priya is saying, you know, the difference here is that what's best for each player actually depends on what the other player is doing. So it's not a situation like before where whatever the other player is doing, I want to play the same action. So the solution concept we use to solve the Prisoner's Dilemma isn't going to help us here decide what's the right thing to do. And in order to solve this game or to reason about what rational players would do, what we're going to do is rely on this well-known concept of Nash equilibrium. So can you raise your hand if you know the definition of Nash equilibrium already? Okay. Interesting. So actually very few of you. I was expecting more people. That's great. I'm really happy to be the first person to tell you about this concept because it's really a brilliant concept. So for each player's, so we say that a player's strategy, in a Nash equilibrium, what happens is that each player's strategy is a best response to the strategies of the other players. So informally, what this means is that if given what everybody else is playing, there's no other strategy. If I could unilaterally switch to a different strategy, there's no other strategy that would give me higher utility than what I'm playing right now. Okay, so for each player, that player cannot get a higher utility if they unilaterally deviated to a different strategy from what they're playing in the equilibrium. So formally, a Nash equilibrium is a vector of strategies, S1 to Sn, such that the following property holds. So for every player I, and for every strategy Si prime that I could switch to, we have the property that the utility of I under the vector of strategies S in this equilibrium is at least the utility of I. So what is this saying? This says when I plays the strategy Si prime, and everybody else, this S minus I means everybody except I is playing the same strategy that they play in S. Okay, so this is notation that we're also going to use later on and in the homework. So again, this is a vector of strategies for all of the players except player I, where they play the same thing that they play in S. So this thing is a vector of strategies where I plays Si prime and everybody else plays what they play in S, Sj. This is a vector of strategies where everybody plays Sj, including player I. Right? And again, what this says is for every player I, every strategy he could switch to, his utility in S is at least his utility when he switches and everybody else plays like before. So that's a Nash equilibrium, and we're going to spend some time thinking about this and practicing this. Okay, so here's an easy poll. You may miss my easy polls after the brutal polls of Zico. I have to admit that even I struggle a bit with some of his polls. These polls are really brutal. Okay, so the poll is, we're going back to the professor's dilemma. And the question is, how many Nash equilibria does the professor's dilemma have? And for those of you who have seen Nash equilibrium before, I'm not talking about mixed strategies yet, just about pure strategies. Okay, I haven't introduced these terms yet, but in case you've seen Nash equilibrium, take that into account. And the question is, how many Nash equilibria does this game have? Let me open the poll. Okay, excellent. So we have a big majority for the correct answer, which is 2. Would somebody like to say which are the 2 Nash equilibria? Excellent. So I was saying, the 2 are make effort and listen, and sleep and slack off. So let's see if, just to illustrate the concept a bit more, if we're in this entry, right? Then if each player deviates, so player 1 can deviate here, or player 2 can deviate here, but of course they get less than 1 million, so that wouldn't be a beneficial deviation. If we're here, so now what happens? Any one player can't go here. It's like player 1 can go here and get -10, or player 2 can go here and get -10. Right? So there's no beneficial deviation. On the other hand, these 2 are not Nash equilibria, because, for example, if I'm slacking off, you don't want to listen, you want to deviate here and sleep. And similarly, if you're sleeping, I don't want to make an effort, I want to slack off. Okay, so out of the 4 possible strategy profiles, 2 of them are Nash equilibria and 2 aren't in this game. Cool. So I want to take a minute to tell you another kind of nice story. So this story, I guess, dates back to when I first taught at CMU. So I started here in 2011, and the first course I taught was actually Grad AI in spring 2012. That was the only time I taught this course before this one. So I had a lecture on game theory, and I was like, okay, I want to teach Nash equilibrium. What would be nice to show? And I remember that there was this movie, A Beautiful Mind, which is a movie about John Nash. I mean, John Nash, in case you don't know about him, is a very colorful figure. He won the Nobel Prize in economics and did many important things in math, but he was also he had mental disorders, and the movie sort of focuses on those aspects. So it's sort of a nice movie starring Russell Crowe. In particular, there's one scene in the movie before he goes crazy, where he's sitting with his buddies in Princeton in a bar, and then he has this epiphany, and he comes up with the concept of Nash equilibrium. So I thought, wouldn't it be nice to show the scene when I talk about Nash equilibrium? So let me show you the scene. A disclaimer is that it's a very sexist scene, so I apologize for that, but I still think it's interesting.
Coming, gentlemen. Deep breaths. Yes, you might want to start shuffling your papers for 5 seconds.
I'm not buying you gentlemen beer.
We're not here for beer.
Anyone else feels she's been moving in slow motion?
Does she want a large wedding cake? Did you say swords, gentlemen? Pistols at dawn?
Have you remembered nothing? Recall the lessons of Adam Smith, the father of modern economics.
In competition, individual ambition serves the common good. Exactly. Every man for himself, gentlemen.
And those who strike out are stuck with their friends.
I'm not going to strike out.
You can lead a blonde to water, but you can't make a drink.
I don't think he said
All right,
that.
nobody move. She's looking over there. She's looking at Nash.
All right, he may have the upper hand now, but wait until he opens his mouth. We lost him.
Adam Smith needs revision.
What are you talking about?
We'll go for the blonde. We block each other. not a single one of us is going to get her. So then we go for our friends. They will all give us the cold shoulder because nobody likes to be second choice. But what if no one goes for the blonde? We don't get in each other's way, and we don't insult the other girls. It's the only way we win.
Okay, I just stopped it just in time because the next thing is going to say is really horrible. Yeah, okay, so this is, so I looked up the scene, right, and I still like to show it, but the really funny thing about the scene, except for being sexist, is that it's, what they're talking about is not a Nash equilibrium. Okay, because, what's the situation they're describing? So there's, every player is facing two alternatives, a more preferred alternative and a less preferred alternative. And what he's saying is, if we all choose the more preferred alternative, then nobody gets the more preferred alternative. Therefore, we should all choose the less preferred alternative. But of course, this is not an equilibrium because then any one player would want to deviate and choose the more preferred alternative. Okay, so what they're describing, it's not clear what this is, but it's not a Nash equilibrium. So when I realized this, I was very excited, and I was actually blogging at the time on this blog called Turing's Invisible Hand. So I wrote a blog post called Russell Crowe Was Wrong, and talking about like this scene in the movie, and giving the whole story. And then one of the comments was by an economist who basically said, you silly computer scientist, you completely misunderstood it. They're not talking about Nash equilibrium, talking about a different notion introduced by Nash called the Nash bargaining solution. Now the thing is, the Nash bargaining solution satisfies a couple of properties. One of them is a property called Pareto efficiency, which means that the outcome is such that there is no other outcome that is at least as good for everybody and strictly better for at least one player. But of course, this outcome, again, that they're describing is not Pareto efficient, because when a player deviates the more preferred alternative, everybody is at least as well off, that player is better off. So this is not the Nash bargaining solution either. Like, it's completely unclear what the scene is talking about. So, that was kind of amusing. And then, of course, a few months later, it was discovered this wasn't like my own discovery. This was known for a while. And in fact, there's an XKCD comic talking about this exact thing. So I'll give you like a minute to take a look, and we'll move on. Okay. I think it's only funny if you know who Feynman is. So this is Richard Feynman, who's a really famous physicist. Okay. So now we can actually go back to our ice cream game and finish the game, and now we can sort of, we have the tools to analyze what will be the outcome of the game. So remember the point where we left off is Teddy got clever and was like, oh, I'm going to set up at the 1/2 point, and then he's stealing most of the customers. So then, day 3 of the ice cream wars, we're like, okay, we'll get clever now and we'll set up at like the 75% point. But then Teddy is again cleverer and sets up south of us. So again, like we're like at the 3/4 point. He's like just south of us, so it gets almost 3/4 of the customers. That's also bad. So we're like, oh, we'll do the same thing. We'll just set like a bit south of Teddy. So this kind of war can go on for a while. And eventually, what would happen is every time when one of us is not at 1/2, right? So let's say one of us is north of 1/2, the other one can set up just like a bit south of the other player and get the majority of the customers. And if one player is south of the 1/2 point, then the other one sets just a bit north and gets more than 1/2. So, these deviations can continue, and eventually the point where deviations would not be possible is when both players are exactly at 1/2. Right? So at that point, both players are getting 1/2 of the customers. And of course, if one player deviates, they're going to get less than 1/2 of the customers. So if one player deviates north, the other player will get all of the customers south of 1/2 and some of the customers north of 1/2. So this is a Nash equilibrium in this game that we talked about initially. We split the customers 50-50, and everybody is happy. Now this is actually a nice, this is a nice little game, but this is again a game that people have sort of drawn pretty grand conclusions from. The model is called the Hotelling model, and it's a model dates back to the early 20th century. One of the things that it tries to explain is why competitors open their stores next to each other. Right? So you often see like there's like the area of Chinese restaurants, Chinatown. Why would everybody want to set in Chinatown? Like you could say, oh, maybe if I set up in a different part of the city, I can attract more customers. But these kind of models are the kind of models that are used to explain it. Right? So what actually happens in equilibrium is everybody sets up shop at the same place, and they basically split the customers. So this is, of course, that model is assuming the quality of everybody is exactly identical. Of course, in restaurants or other kind of businesses, it wouldn't be like that, but that's just one basic model that people use to reason about this phenomenon. Cool. Okay. Good. So, this is actually going a lot faster than I anticipated. So I want to tell you about a more complicated game now. This is the famous rock, paper, scissors game. And this is again a game that I think a lot of people know from their childhood. A lot of us played it in order to settle disputes with siblings. And the way the game works is every player, there are two players. Each player has three strategies: rock, paper, or scissors. And the way it works is if both of us play the same strategy, there's a tie. However, if one plays rock and the other plays scissors, then rock wins. Rock breaks scissors. If one plays scissors and the other plays paper, then scissors beat paper. And if one plays paper and the other rock, then paper beats rock. Okay, so that's sort of the way to remember it. That's how the game is defined. And as a game in normal form, here's how we write it. So each player has the strategies rock, paper, scissors. And then you get a payoff of 1 if you win, a payoff of -1 if you lose, and a payoff of 0 if there's a tie. So what do you guys think? Is there a Nash equilibrium in this game according to what we talked about so far? If yes, what is it? If no, why not? Jonathan?
There isn't one, because every strategy, the other player can always move to a different move to beat the other strategy.
Excellent. All right, so Jonathan is saying there isn't a Nash equilibrium. And his reasoning is that whatever the two strategies are, a player can always deviate to a strategy that beats the other player. Right? So for example, if you take rock and scissors, right? So rock beats scissors, but scissors could deviate to paper and beat rock. Right? So whatever the losing player is doing, there's always a strategy that beats the other player. So they could always deviate and beat the other player. Even if there's a tie, if we're both playing rock, again, I want to deviate to paper and win the game. So even if there's a tie, or if you're the losing player, then if there's a tie, both players want to deviate. If there's no tie, then the losing player wants to deviate to a winning strategy. But no matter the situation, for every combination of strategies, it's not going to be a Nash equilibrium. One of the players will want to deviate. Okay, so again, remember we started from dominant strategies, and we said, this is great because we can reason about what players will do. But then we talked about the professor's dilemma where we couldn't solve it with dominant strategies. So we said, let's look at this brilliant concept of Nash equilibrium that allows us to reason about what the players will do. But now again, we're stuck, right? Again, now we can't reason about what the players will do because there's no Nash equilibrium in this game. So in order to reason about this type of game, and this will be the final relaxation that we have to do in order to be able to reason about any game, the idea is that let's give the players more options. And this is really, this was the brilliance of Nash's idea, the epiphany that he actually had, and what it led to. So the idea is, let's let players randomize over strategies. So far, we talked about what's called pure strategies, which is, there's some strategy set, and you have to choose, a fixed strategy. So now we're saying, let's allow players to play mixed strategies, which are probability distributions over pure strategies. So, for example, in the rock, paper, scissors game, I can say, I want to play rock with probability 1/3 and play scissors with probability 2/3. That would be a mixed strategy. So that gives us, as players, a lot more things we can do. And in terms of, so it expands the strategy spaces and also expands the set of strategy profiles that can potentially be Nash equilibria. So a bit more formally, we're going to denote the mixed strategy of player I by xi, where for a strategy Si, xi of Si is just the probability that I plays the pure strategy Si. Okay? So xi is basically a vector of probabilities, one for each possible strategy, that tells you the probability that I plays any possible strategy in the set S. Okay, so is this definition clear? So we're just saying, all we're saying is now players, instead of choosing a deterministic strategy, are allowed to randomize when they choose their strategy. And the utility of player I, so we're just going to redefine the notion of utility. Before which we said we have a utility function ui that takes as input strategies and outputs the utility of player I for that profile. So now I'm just going to overload the notation ui, but I'm saying now it can get as input mixed strategies, x1 to xn, so these are probability distributions. And the output is basically the expected utility of I based on these probabilities and the utility function ui. Okay? So what this is saying is, look at all possible strategy profiles, all combinations of strategies, and I'm going to take the utility I get for the strategy profile and multiply it by the probability that each player plays as a signed strategy, which is the product of xj, sj. Okay? So again, this is the probability of this strategy profile, and this is the utility of I in that strategy profile. So this is nothing but the expected utility of I in this mixed strategy profile. Dimitris?
Can you go back to the slide where you define UI?
Sure.
Just remind us the definition of UI of X.
Yep. All right, so this is the definition of UI. So UI is just a given function. Okay, and it just tells you, so it takes as input a vector of length n of deterministic strategies, of pure strategies, and tells you the utility of I when everybody plays that way. Okay? And now, so now we actually use like the same function UI. I'm sorry, like I said, I'm overloading notation. But what I'm saying is the function UI tells me for every pure strategy profile what the utility of I is.
So there is also like a vector of use, which is the utilities of all the players.
Yes, yes. So that's part of the specification of the game. Right, so for each player, part of the game is we're given the utility function UI. Right. Yeah.
So these numbers xi, are they real numbers?
Yeah, the real numbers.
So they cannot depend on the strategy?
Are
they fixed before?
No, so I mean the idea will be the player is going to look at the game and decide on a mixed strategy. So decide on these probabilities xi. Okay, so before we were saying I'm looking at the game and I'm deciding to play rock with probability 1, like I'm definitely playing rock. So here the idea would be I'm looking at the game and now I decide to play rock with probability 2/3 and scissors with probability 1/3. So we'll have xi of rock as 2/3 and xi of scissors.
Say something like xi of rock is 2/3
yes.
if the other player is...
Oh, no. Yes, I'm not allowed to condition what the other player is doing. Yeah, we'll actually talk about a type of game like that called the Stackelberg game in the next lecture, where first one player is playing and then like the other player responds to that player. But this is a very important point. So here, it's like in rock, paper, scissors. Like if you've ever played it, like you have to, play at the same time. So you do like that, and then. So the idea is like these are all of these normal form games are trying to capture cases where players simultaneously make their move. We'll also talk about extensive form games later, which are sequential games. But here again, like these are simultaneous, so we have to choose our strategies without knowing what the other player is going to do. Okay? So it's again like the situation that you have in rock, paper, scissors. Like if you knew what the other guy is doing, you just say, oh, if he's playing scissors, I want to play rock. But he would also be saying, oh, if he's playing rock, then I want to play paper, and this would never end. Right? Okay. Good. So is everybody okay with like this definition of how we define mixed strategies and the utility? So just, it's really simple, I think. It's just like utility is the expected utility under the function UI when we play these probability distributions. Good. Okay. So let's go back to the rock, paper, scissors game. And let's spend a bit of time like thinking about this game and practicing this definition. So let's say that player 1 plays the mixed strategy 1/2, 1/2, 0, which means it's playing row 1 with probability 1/2, so rock with probability 1/2, row 2 with probability 1/2, so paper with probability 1/2, and scissors with probability 0. So it's 1/2, 1/2, 0. Player 2 is playing 0, 1/2, 1/2, so he's randomly choosing between paper and scissors. And the question is, what is the utility of player 1, the row player, when they play the strategy profile? That's a question to you guys. Sorry? Say again? A quarter. I think it's close, but not quite. Yeah. So the second player would have 1/4, but the first player would have a somewhat different utility, -1/4. Okay? So let's see what happens. So we're looking at so basically we're saying player 1 plays 1/2, 1/2. Player 2 plays 1/2, 1/2. So basically, the possible outcomes are these 4 entries of the matrix. And we're looking at the left number, we're looking at the utility of player 1. So what we're getting is -1 with probability 1/4, 1 with probability 1/4, 0 with probability 1/4, and -1 with probability 1/4. And then the expectation is -1/4. Okay, here's another question. So if both players play 1/3, 1/3, 1/3, so basically each player chooses a strategy uniformly at random, what's the utility of player 1? Zero, great. So would somebody like to give an intuitive explanation for why it's 0? Dimitris?
Every box is possible with probability 1/9.
Excellent.
And in every row and every column there is exactly 1/1. That cancels the -1.
Excellent. Right, so Dimitri is saying, so what we get with 1/3, 1/3, 1/3 is we get a uniform probability distribution over the entire matrix, so probability 1/9 for each of the possible entries. And then, like Dimitri said, if we look at the utility of one player, there are 3 1s, 3 -1s, and 3 0s. So the 1s and -1s cancel out, and we end up getting 0. But also, I think it's very intuitive because of symmetry, right? We're just saying, like, it's a symmetric game. Both players are playing the same strategy. So it can be the case that, it's also, we'll talk about this in more detail. This game is called a zero-sum game. Like, the utilities of the two players add up to 0. So somehow, if they're playing the same thing and it's zero-sum, the only thing that can happen is like 0 to both. Otherwise, like, why would one player have an advantage? And yet another way to see this is thinking about it the following way. So if the other player, let's even argue something stronger. So let's say if the other player is playing uniformly at random 1/3, 1/3, 1/3, then whatever I play, I'm going to get utility 0. Right? And the other guy is going to get utility 0 as well. Because if I choose rock, then I'm going to win with probability 1/3, lose with probability 1/3, tie with probability 1/3, and the same goes for the other two strategies. Right? And now if I randomize over the strategy, so let's say, okay, I want to be smart, I'll take rock with probability 1/3 and scissors with probability 2/3. So now with probability 1/3, I get utility 0. With probability 2/3, I get utility 0. But it's not going to help me to randomize when every action that I take gives me expected utility 0. Okay, so it's sort of even a bit more than that in a sense. Okay, good. So now this poll should be pretty easy. Poll number 2. So for this game, which of the following strategy profiles is a Nash equilibrium of the game? Great. So we have, again, like a very nice majority for the correct answer, which is 1/3, 1/3, 1/3. I guess I sort of gave it away when we talked about the previous slide. I got excited and talked too much about that strategy. Okay, so just to recap, so we're saying 1/3, 1/3, 1/3 for both players is a Nash equilibrium because when the other guy is playing 1/3, 1/3, 1/3, whatever I do, I'm going to get 0. Right? So there's no point in deviating. Every strategy gives me 0. Even if I take some distribution over my strategies, I'm going to get 0. And this is true for both players, so this is a Nash equilibrium. But let me ask you like a slightly harder question. So for example, if you look at answer number 1, 1/2, 1/2, 0, 1/2, 1/2, 0. So can you tell me why this is not a Nash equilibrium? Ashwin?
You can always...
Ankush, sorry.
You can always, like knowing the other player's strategy, you can just play like the winning strategy corresponding to that strategy with the same probability distribution.
But here you don't know, so all you know is the other player is randomizing with probability 1/2 between rock and paper. But so you don't actually know what they're going to play.
Yeah, but we know the
Alex?
probability distribution, so
Yeah.
we can change our probability distribution to, let's say, 1/2, 0, 1/2, or put 0 in another position such that you get +1/4 as we computed already.
Okay, so what specifically would you want to play? Sorry?
Increase your expect value of 32.
Yeah, but so what would you propose playing? Yeah, Nikhil? Excellent. Right, so Nikhil is saying, here's a specific proposal for how you deviate. So we're both playing rock and paper with probability 1/2. Our expected utility for both players is 0. So Nikhil is proposing let's let one of the players, us, right? We deviate to paper. So what happens is with probability 1/2, the other guy gets paper and we're tied. With probability 1/2, the other guy plays rock and we win. So our expected utility will be 1/2 instead of 0 like before. Okay. Right. So definitely, like there is a deviation for each player that makes that player better off. And more generally, it's not hard to show that randomizing uniformly at random is the only Nash equilibrium in this game. And it could be a nice. I mean, if you guys are bored at home, like you could do this as an exercise. But essentially, the idea is if some player is playing a strategy with probability more than 1/3, then basically I can exploit, like the other player can exploit that strategy by playing the strategy that beats it. So the other player would sort of want to play deterministically, but then that can't be an equilibrium because when one player plays deterministically, the other player wants to play the strategy that exploits that strategy. So that's on a very loosely the kind of reasoning that you can use to prove that 1/3, 1/3, 1/3 for both players is the only Nash equilibrium in this game. Okay, so what we just saw, again, let me recap. So we said our last problem was that in rock, paper, scissors, there was no Nash equilibrium in pure strategies. And then we said, let's talk about the epiphany of Nash. You actually can use mixed strategies. And then we can redefine the notion of equilibrium for mixed strategies. And now for this game, thankfully, we have a solution, which is, like we're saying, rational players would uniformly at random randomize between rock, paper, and scissors. But the beautiful thing about what Nash was able to establish is that it's not only relevant to rock, paper, scissors. Like I said before, this is the last relaxation that we actually have to do. What he showed is that in any finite game where the strategy space is finite, there are many variants of this, but we're sticking to finite games, there exists at least one, possibly mixed, Nash equilibrium. So if you allow mixed strategies, there's always going to be a Nash equilibrium in every possible game. So this sort of says, Nash equilibrium can always be used to reason about what players will do. As we'll see in a few minutes, you can argue whether it necessarily gives the right solution, but it gives some solution that in many cases is the intuitive one. So I think in rock, paper, scissors, it's very intuitive to say, if players are sort of playing at random. So this is Nash's theorem. It's important. It's also going to play a role in the homework. But let me just make a few comments about computational aspects. So in the next few lectures, we'll talk about some other solution concepts and other games, and we'll talk quite a bit about computation and algorithms. With Nash equilibrium, I actually don't want to devote a lot of time to this because the computational questions related to Nash equilibrium are very complicated. But I just want to give you like a high-level overview of what's known. So there isn't a sort of classic algorithm for computing Nash equilibrium due to Lemke and Hausen. And it's actually very reminiscent of the simplex algorithm. And it sort of works like reasonably well in practice. And for a long time, it wasn't known whether this algorithm actually runs in polynomial time or not. So I think this question was settled around 2003 or 4. So there was a paper giving a counterexample, showing an example where the algorithm wouldn't terminate after a polynomial number of steps. But then the next step was actually even more exciting. So in 2006, there was a paper by Paul Goldberg, Kostas Daskalakis, and Christos Papadimitriou, where they showed that computing Nash equilibrium was actually hard for a complexity class called PPAD. Now, why PPAD and not something like NP? So this is an interesting point and part of what makes this complicated. Right, so NP is a class of problems that talks about decision problems. Right, so it's like the answer is either yes or no. Now with Nash equilibrium, the natural decision problem is there a Nash equilibrium in the given game? But this is a very easy problem because the answer is always yes. Right? I mean, from Nash's theorem. So of course, this is not the problem we're interested in. Often there's a lot of work on this, but often the answering the decision problem is as hard as finding a solution. Okay, I mean, not always, but often. There are cases where there are separations, but here it's an even weirder situation because the decision problem is moot, like it's not interesting at all. So the only interesting question is the search problem of actually finding a Nash equilibrium. So PPAD is a class of problems designed to reason about problems that always have a solution, and the hard part is actually finding a solution. Without going into more details, that's basically the situation. So this reduction, this result basically means that people believe strongly that there's no polynomial time algorithm for Nash equilibrium. So the idea is, they reduced from a different problem where it's sort of very intuitive that there's no polynomial time algorithm for solving that other problem. So that's the situation. Okay, so that's all I'll say about computation of Nash equilibrium for now. Matthew? PPAD. And a running joke is that people thought that when Papadimitriou introduced it in 1995, people said, "Oh, it's just using all of the letters in his name to define this complexity class." But his response was like, "If you ruled out all of the letters in my name, that you'll be left with no letters at all." So there's sort of no getting around it. Okay, any other questions about computation of Nash equilibrium? Cool, so I just have one last slide, but it's actually a very interesting discussion, I think, so we can easily spend like 7-8 minutes on this. So like I said, Nash introduced this concept in 1950, and it's been like a transformational concept and is all over economics these days in many different variants. But in some games, Nash equilibrium actually doesn't make sense. So it doesn't give you the solution that you would expect intuitively. And I want to give you a really nice example of such a game. So here's the game. We have 2 players, and the strategies are the integers 2 to 100. So every player chooses an integer between 2 and 100. Now the rules are, if both choose the same number, they both get that number. If one chooses s and the other t, and s is smaller than t, so if they choose different numbers, then the one who chose the smaller number s gets the smaller number plus 2, and the one who chose the larger number t gets the smaller number minus 2. Okay, so if s is smaller than t, s gets s plus 2, t gets s minus 2. Yeah.
Someone chooses 99 and the other 100.
Yeah.
The first one gets 101.
Yes. Yep. Okay, so here's an example. If one chooses 99 and the other 98, the 99 would get 98 minus 2, which is 96, and the 98 would get 98 plus 2, which is 100. Okay, now what I want you to imagine is, let's say that I told you that I'm going to pair you up with a random other student in the class, and you both choose. So I'm going to ask all of you guys to choose strategies. But when you do this, imagine that I told you that I have decided how to pair all of you up, and then I'm going to look at what you chose and what the other person, your partner, chose, and I'm going to pay you both that number, the number that you get in dollars, or in like thousands of dollars, or in millions if you want to make it really interesting. So, right, and then the question is, what would you choose? So this is a question with no right answer. So I actually didn't even include the option beats me in this poll, because you don't get to say, like, I don't know. There's no right answer. Okay, so I want everybody to think about what they would do in this situation.
How much time?
Yeah, let's take like 3 minutes. Okay, very interesting. So a lot of you chose 100. So somebody who chose 100, can you explain why you chose 100? Yeah, Ashwin?
So, you can't, if you pick, so there's no sense in picking anything less than 98, because if you pick 100 and the worst that you can get is 98.
Well, no, I mean, you got the smaller number minus 2. So, for example, if the other guy chose 80, you get 78.
He gets 82.
Any other arguments? Yeah?
I think if you try to optimize for yourself, so you assume that the other guy plays 100, and you try to be smart and you play 99, play for 101, the other guy will do the same, and you will both repeat this argument till you end up choosing 2. But if you both choose 100 and you are happy with making both of you 100,
I mean, that's a very nice reasoning. I mean, the only problem is, like, you can't actually coordinate with the other person, right? So you're saying,
but you assume that he's...
well, maybe it's one of these people. Yeah, Alex?
Actually, like what you just said is that you basically have 2 choices, either 2 or 100. And then it's kind of your psychological belief of, do you want to be stable or do you want to risk?
Okay, very interesting. So let's just formalize like this reasoning that you guys have given. Why 2, right? Why are Demetrius and Alex saying 2? So I think the reasoning is, it's called iterated elimination of dominated strategies, and you'll actually have a homework problem about this exact thing. So the idea is the following. I first want to claim that you never, I actually think 100 is, if there's one answer that is not right, it's 100. And I guess so the reason is, you really, like, at the first stage, you never want to play 100. Because no matter what the other guy is doing. Because if the other player is playing, so let's compare 99 to 100. I want to argue that 99 dominates 100. If the other person is playing 100, if you play 100, you get 100. If you play 99, you get 101. Okay? If the other guy is playing 99, if you play 100, you get 97. If you play 99, you get 99. So you're also better off. If the other guy is playing 98, it doesn't matter if you're playing 100 or 99. So whatever the other person is doing, it's always better to play 99 than 100. Okay, so it's sort of very... I think this is like a pretty convincing argument saying, you shouldn't play 100. And actually a lot of you guys chose that answer. The problem is, as people were saying, like, once you start applying this reasoning, you end up with 2. Why? Because now you're saying, okay, nobody ever wants to play 100. But now, once you eliminated 100, 99 is dominated by 98 by the exact same reasoning. So we can say, so nobody will ever play 99. But now 98 is dominated by 97. And if you continue this reasoning, the only thing that ends up, you just go all the way down to 2, which is the minimum. So this game is solvable by iterated elimination of dominated strategies, which is what we just did. And what we'll show in the homework is that if iterated elimination of dominated strategies leads to a situation where each player only has one remaining strategy, then that's the unique Nash equilibrium of the game. Okay? So this you'll prove in the homework, but the bottom line is the only Nash equilibrium in this game is when both players play 2 and get 2, whereas, obviously you can do much, much better. So the really interesting anecdote about this game is that people have tried asking different groups of people to play this game. So, when you let people who are sort of normal people play this game, people often play strategies, in the 90s or close to 100 and end up with a very high payoff. But when people have run this experiment in a game theory conference, and then most people chose 2 and ended up with 2. So and again, part of the reasoning is you'll be paired up with the game theorist who's going to apply all of this reasoning. So you're we have to choose 2. So the game theorist actually ended up with much lower payoff than normal people. So this is pretty bad, and I think it sort of partially says, in some sense, that Nash equilibrium really is not the right solution for this game. And there are many examples of games where it just gives pathological outcomes. Okay, great. Any last questions? Okay, see you on Monday.